Hello and welcome to the section where we're going to introduce some more detailed understanding of a bipolar transistor and its importance in an analog context. In this slide I've shown the basic structure of the two types of bipolar transistor, an NPN at the top and a PNP at the bottom. Now both types of transistor have got three zones made up of differently doped materials, different types of materials with different polarities. So in the top one, the NPN, which is by far and away the most common in analog circuits, we see we have an N plus a highly doped N region around the emitter. So that's rich in mobile electrons. We have the base area, which is more lightly doped P region. So that's a region where predominantly we're looking at holes as the carrier of the charge, and the collector region at the bottom. So this NPN structure is made up of these different zones, and at the interfaces between these zones we effectively have a diode. So between the N plus emitter and the P region of the base we've got a diode, and another diode between the base and the collector. And what's important in the transistor operation is the way that we can use the current that flows into the base to control a much larger current between the emitter and the collector. It's exactly the same really with the PNP transistor, but I'm going to concentrate most of my discussion on the NPN so that we can focus on that type and understand that very clearly. As I've said in the previous slide, what's really important with the bipolar transistor is how the current that you induce into the base can produce a much larger current flowing between the collector and the emitter. So we see here, for example, our base current affecting the junction between the base and the emitter. That then produces a much larger current that flows from the emitter through the base and down to the collector. And it's this basic process where a small base current controls a much larger current flowing from the emitter to the collector that actually creates the possibility of amplification and all of the interesting other circuit properties that we can get from the transistor. Now we can think about these very interesting transistor devices in different ways, but what I'm going to first do is look at the basic operation, the so-called large signal operation of the bipolar transistor. And once we've understood that, in future sections we'll look at how we use that to generate amplification of a signal, for example, by moving more to what's called a small signal model. But in this case we're going to start with the general operation, the large signal operation. So as we've discussed, what's really important is this use of the base current to create a much larger current flowing between the emitter and the collector. Now when we do a conventional circuit diagram, we generally draw positive current because that's the way that historically we started to draw electrical circuits. So in this diagram, for example, on the left I've got an NPN transistor. My base current comes into the base and it controls the much larger current, the conventional positive current flowing from the collector to the emitter. And what I've represented in this circuit is that I can represent that much larger circuit by a so-called current source. And I've ringed in red on the slide the current source, which is a feature really of the forward conduction, the IF forward conduction of the diode in that part of the circuit. And what we'll move on to is look in more detail at how we calculate that forward current and therefore the amplification of our transistor. What we can do is use Kirchhoff's circuit laws to write some relationships between the currents that are flowing in through our NPN transistor. The emitter current is really just the IF, the forward current of the diode. The collector current is related to that, but we have to consider the amplification factor, alpha F, which is the amplification factor of the diode. We'll come to that in more detail in a minute. But we can immediately note that the base current is just the difference between these two, the emitter and the collector current. So that final third equation there is a very fundamental equation about the bipolar transistor and must always be true. In terms of the diodes that make up the transistor, we already know from basic theory of diodes what those currents will be. They're just related to the barrier in the diode, the thermal voltage, and they relate through these equations known as the Shockley equations, which tell us what the forward and reverse current of the diode would be. In normal operation, we're just dealing with the forward current of the diode, but in some cases we will consider the reverse currents as well, but by and large we're going to concentrate on the forward currents. Now there must be a relation between the collector current and the emitter current, because that's fundamental to the operation of the transistor. The current flows through from the collector to the emitter, and so therefore they must be related. And they're related through this concept alpha F, which is the forward current gain. And that's simply the ratio of the collector current to the emitter current. Now in a good transistor, that ratio is almost 1. It's very close to 1 because we see the current flowing directly from the collector to the emitter. What's often more important is what's highlighted in this slide, the relationship between the collector and the base current, and we call that beta F, the forward gain of the transistor. And this is commonly the number that is quoted about transistors. In a good transistor it might typically be somewhere between 100 and 200, for example. Because we also know fundamentally from Kirchhoff's laws that the base current is the difference between the emitter and the collector, we can use that information, as we've done lower down in the slide, to relate that beta F to not just the collector current but also the emitter current as well. And we can therefore obtain a direct formula, for example, that involves just those two quantities. Those are easily measurable in our circuit, and therefore we can calculate the gain directly from measurements if we wish. Now obviously there's also going to be a relationship between these two gain factors, between them the beta gain, which is the main gain that we usually work with, and alpha F, which is the gain, the forward gain of the current as well. And the final equation on the slide relates those two together, that beta is equal to alpha F over 1 minus alpha F. So that must also be true. So if we know beta, then we can always calculate the alpha as well. But as I've said, generally in a circuit, we're mostly interested in the beta value, and that will typically range between 100 to 200 in most common bipolar transistors. Now that's given us some basic equations which we can relate the different currents of the bipolar transistor to each other. And let's have a look what happens when we use a bipolar though, and we start to drive it and we start to connect it up to measure the currents that we see. So on this slide you can see a number of graphs which show you how the transistor will respond. So in the left hand side we've got a graph of the collector current versus the voltage VBE between the base and the emitter. And what we see there is very little current until we get to around about 0.7 volts in this graph. This is because I'm really drawing a graph for a silicon transistor, and what happens there is that once I get that voltage to around about that value, the diode becomes operational. That's the barrier inside the diode that I'm now overcoming, and my current then starts to flow. I can see that in more detail on the second graph, which is the same information but presented on a logarithmic scale for the collector current. What you can see there is that because I've got a logarithmic scale, I can now see the small values more easily, and I can see that actually as the VBE value increases, my current rises exponentially. That's a straight line or a logarithmic curve, and that's the formula that I saw in the Shockley equation, where I saw an exponential related to the VBE value. The third graph shows a relationship between the collector current and the base current. And the first thing here is important to notice the scales are different. The base current is in microamps, the collector current in milliamps. And that's because I've got a gain of maybe at least 100 between the two values. What you can see is that as my base current goes up, my collector current goes up as well. And it's a nice linear relationship in this curve, which is what I want. So as I pump current into the base, my collector current turns on, and that's now enabling me to amplify the signal, because I can see that I've got a lot more collector current than I'm using in the base, and that's the essential basis of the amplification of the transistor. It's also important to look at how the transistor behaves as we vary the voltage between the collector and the emitter, and that's what we're showing here on this slide, where we've got two graphs. The first graph on the left hand side shows how the collector current varies as we increase the voltage from base to emitter in steps of 0.05 volts, so 0.7, 0.75 and so on. And what you can see is that the current increases, the collector current increases, but it increases in a non-linear way, and that's because those VBE voltages are controlling the diode, and the diode is inherently an exponential thing. It's not a linear device. So we see the current rising increasingly as that voltage gets bigger, and we can see that because the gaps between the lines on that graph are getting wider as the VBE voltages increases. I've also marked on the graph two regions of the graph, if you like. There's the first part where the current rises rapidly from zero, and then it plateaus out into an area, and we generally call that flattish area on to the right of the graph the active area, because that's mostly the region we're going to use when we come to design circuits. We call that rapidly rising area the saturation area, because that's where the diodes are moving into saturation. On the right hand side of the slide, I presented the device for the same information for the same device as a function of not of voltage now, but of base current. And what you can see is that as I control the base current in steps of 1 microamp, then the current rises, but this time the distance between the lines is the same, and that's because the device is a linear in the base current. And that's actually a much better way for me to control the properties of this device, by using a current control where I get a linear response, than if I go for a VBE type approach where I have an exponential non-linear approach. So I much prefer to use my base current as the controlling mechanism for my BJT. Now this device data is taken from a very common device which I've listed in the top right hand corner here. This is a sort of catalogue device that you might well use in a project work, for example, to give you some data from a real device rather than just a theoretical device. So as I vary these voltages between the base and the emitter, VBE, and between the base and the collector, for example, then the device will go into different regions of operation. Now, the region that I normally want to use is this active zone, which I've coloured green on the charts here, and that's where we have a VBE in forward bias, so we're bringing current into the base, and we've got the right polarity of voltage between the collector and the base. There are other regions. Now in general I'm not going to operate my devices in an analog circuit in these other regions, so there are three other possibilities of the combinations here. There's a saturation region, as we've shown on the graph, where the current is rising very rapidly. Difficult to control the current in those areas, so that's the reason why I don't use it. But I've also got a reverse situation where I've got the device effectively in a reverse bias situation for VBE, and I've also got an off region, the cutoff region, where I've got the polarities incorrect essentially, and I've got no transistor, I've got no current flowing, so I've got an open switch, if you like, in terms of that kind of way of representing it. So as I said, generally I want to be in the forward active region where the device current is well controlled by the base. I can control the base current very easily by the circuit. That then gives me very good control over the transistor, and that's generally the region that I'll operate the device in for most of my analog circuits. So as we've said, there are a number of regions of operation of the bipolar device. I generally want to be in the active region, the active operation region, but sometimes I might use the saturation region in a few circuits, but generally speaking I'll be in the active region. And what determines that obviously is these bias voltages that I apply across the transistor, and also the current that flows into the base and so on. Now these currents are of course affected by the external circuit as well, and that's really how we design a circuit and control the transistor operation. So let's start to introduce some components into this and think about, for example, a resistor in series with the collector and to the emitter current as shown in the diagram. So my transistor operation is going to be determined, for example, by the base current that I feed in, or the voltage, if you like, around VBE. But it's also going to be influenced by the RL value as well. So in the active operation, as I've put down on the left-hand side, my collector current is the gain times the base current. That's the fundamental relationship of the bipolar transistor. But in fact, that can only be true if only be true for certain values of the RL. So if RL is the wrong value, then actually then it's no longer enough current flowing to make that happen. So I have to also think about the RL values as well. And it's the same in the saturation current as well, situation as well. In the saturation part, the current is rising very rapidly as it goes from 0 up to the active region, and that's actually influenced obviously by the voltages that I apply, but also it is limited in fact by the RL value. That resistor will limit the current that can flow through the device as well. So as I impose different values of RL, I will see the current flow being affected, not just by the voltages but also by that resistor value as well. Now, one of the ways that we analyze this performance is to do what we call a load line analysis. So let's think about our circuit again, where we've got this resistor RL in series between the collector and the VCC line. I could control the transistor by VBE, for example. Now, of course, in this circuit now, so we're thinking about a circuit, not just the transistor. In the circuit, something will limit the current. And if the transistor is fully on, then that maximum current is limited by the RL value and is going to be actually VCC divided by RL from Ohm's law. So if I then draw a graph like I have on the right hand side, where I've put on top the transistor line, so you can see the transistor curve, you can see that the maximum current level on my load line, shown in red, is this VCC over RL value, and I've put that on the curve roughly as it might be. The other factor that is going to affect it is the so-called cutoff frequency of the transistor. When is the voltage so small that the transistor is no longer on? And that's actually going to be down there on the bottom of the curve. So I end up with a red line that goes from top left to bottom right, and it intersects the transistor line at that point in the middle of the figure, which we usually call the operating point. So my load line analysis is a way for me to represent the action of the circuit superimposed on the transistor curves that I might get from the datasheet. And we'll see as we get into the detailed circuit design that this load line method can be a very useful way of calculating the values of the circuit components. Now, as we look in more detail at how these transistors work, we'll see that they don't always behave in the ideal way that we've seen in our early courses and early analysis. And one of the effects is that, in fact, once we're in the active zone, those curves in the transistor are not completely flat. And I've tried to draw that on this diagram here in the center, where I've got a curve for the collector current versus VCE as I increase IB. So this is like we had in one of the previous slides. Those curves are not 100% flat. There is still a slight dependence of the collector current on VCE in the active mode. And this is actually called the Early effect, after a man called James Early, who was an American scientist who discovered this effect in the early days of bipolar transistor development. And what happens here is that as those lines are not straight, so I've tried you can see now redrawn it on a larger scale, what happens is that those lines actually come back to a point on the left hand side below 0. And this could be at a very negative voltage, like 100 volts, for example. And this effect is a real effect that we can see in some transistors, and it's mainly influenced by the base of the transistor. If the base transistor is very narrow, then we can get a very large gain, but that produces a relatively large early voltage as well. Now, we would prefer these curves to be flat because that gives us a much more of a controlled linear amplification. But unfortunately, there is a slight effect, and we do sometimes have to take this into account in our circuit design. Mathematically, we can include the early effect in our formulas by modifying them slightly. So, for example, the collector current formula is driven really by the diode theory, but actually we can change that slightly by introducing a component dependent on the ratio between VCE and the early voltage VA. So that will enable us to actually calculate that collector current more accurately where we feel that the early current process is in play. And what that also does is modify our gain as well. So our gain changes as well. And we'll see later on that this will also impact the output impedance of the device as well. So these are important considerations in some circumstances where the early effect might actually cause us to redesign our circuit slightly. In terms of our load line analysis, the early effect actually essentially produces two lines, if you like. So I've drawn on the right hand curve two versions of the transistor line, one with the active region flat and one where the early effect is included. And what you'll see is that that early effect modifies the load line as well. So we end up with 2 points where the output varies slightly with load, and this is not really an ideal type of situation. Another effect that we'll see when we look at transistors in more detail is that actually there's frequency effects as well, and that's caused by inherent capacitances inside the transistor. So the doping junctions between the diodes, in effect, between the base and the emitter, for example, that produces a capacitance. And there's also a capacitance between the collector and the emitter. And these capacitances are there in every bipolar transistor, and what they cause is that the gain does depend on frequency. So as you get to a very high frequency, generally you will see the gain decrease. And we usually define a concept called the unit gain frequency, FT. And FT actually relates directly to these two capacitances inside the device. And these are important when we come to think about the high frequency operation of the transistor. So in summary, in this section we've introduced the basic operation of the bipolar transistor. We've thought about the Ebers-Moll large signal model. We've looked at how that affects the way the transistor is controlled, and we've begun to introduce effects like the early effect and the frequencies effect that we see in the bipolar transistor performance as well. And we'll build on this as we then come in the next sections into practical circuit design of some important amplifier circuits.